Hello there guys and welcome back to another video on stochastic processes. In this video, for the first time, we're looking at stopping times. So this is an incredibly important concept for stochastic processes, comes up all the time, so there's no time like the present to get learning it basically. So I'm going to just read you out what I've written. This is a really nice definition of a stopping time, and afterwards I'm going to give you a kind of real world analogy to make it make a bit more sense. So if we say that xn is a discrete time stochastic process, okay, so we can think of xn as a sequence of random variables, x1, x2, x3, and I'm going to say that capital T is a random variable that takes values that are either the positive integers, so 1, 2, 3, 4, 5, 6, all the way up to infinity, and also it could be infinity as well. So your stopping time, t, could actually be just infinity. And we say that t is a stopping time if the following. For all n in the positive integers, it can be determined whether or not the event that t is less than or equal to n occurs from x1, x2, x3, and xn, etc. Okay, and obviously all the ones in the middle. So what does this actually mean? Basically, it's telling you when to stop your stochastic process, okay? So I'll give you a trivial example of a stopping time. Stop the stochastic process when n is the number 10. That's a really boring one, but that is a stopping time. So when you get to 10, stop. Okay, that's it. Here's another one. Let's say that the x's, the xi's, x1, x2, x3, each of those takes the value 1 with probability p, and let's say 0 with probability 1 minus p. A stopping time could be stop the process when you get 2 1s in a row for the first time. Fine, it's a stopping time. Stop when this happens. That's all they are. Stop when this happens. When this happens, when you see this, stop. That's it. Now, there are things that are not stopping times, which we'll get to in a second, and I'm going to transition us to that with an analogy, but that's basically what this is. So basically, for something to be a stopping time, you have to be able to know when to stop when t is less than or equal to n, okay? So you cannot see into the future to know when to stop, okay? And again, you'll see examples in a minute. Here's my analogy to explain that. So let's say that you're driving your car down the road and you don't really know where you're going. So you ask someone, maybe you're trying to get to the nearest supermarket in some random town. And you say to someone, could you please direct me to the supermarket? And basically what you'd like them to do is give you a stopping time, right? Stop when you get to this, or stop 1 mile after this, or something like that, right? That's what you want to get to the supermarket. So that's going to be your, they're going to tell you to do a bunch of stuff and then stop, right? That's how it works. But if someone said to you, yes, to get to the supermarket, stop 5 miles before the third pub, you'd say, but I don't know where the third pub is. So that's not a stopping time, because in order to know to stop, you kind of have to see into the future, because you don't know when you're 5 miles away from that pub, right? You can count pubs, you can go, okay, I've gone past 2 of them maybe, but you don't know when you're 5 miles away from the third one because you haven't got there yet. So a stopping time cannot be something where you can see into the future, because it doesn't make any sense. So you need to be able to know when to stop as soon as something happens. So a good stopping time would be stop, let's say, 5 miles after the third pub. Because you can say, okay, there's my third pub. Now I'm going to drive 5 miles and I'm going to stop. It's so simple, right? But you can't stop before you get somewhere. And basically, this is the underlying logic of this orange/yellow thing here. You need to be able to stop. If you're at, let's say, the nth term of the stochastic process, you need to know when to stop using that information or stuff from before it. So that using the nth term or using the previous terms. Okay, let's look at some actual mathematical concrete examples. Okay, so here's our first example, guys. Let's let xn be a stochastic process where each xi takes the value 1 with probability p and 0 with probability q which is also 1 minus p. This is just called a Bernoulli process because each xi is a Bernoulli random variable, but it doesn't really matter. It's just a simple example. And I'm going to say let t be the minimum value of n such that xn equals 1. So in plain English, what does that mean? Well, t is the smallest value of n so that xn is the number 1. In other words, t is the first time that xn takes the value 1, okay? So n, if p was quite big, in all likelihood, n would just be the number 1 here, right? And that your stopping time would just be the number 1. If p was very small, maybe it would take a bit longer. So t is a random variable. Stopping times are random variables. They take values with various probabilities. So the value of t could be 1 or 2 or 3, or it could be 100 or whatever you want. It depends on the situation. But this is t. The question I'm going to ask you is this a stopping time? And the answer, maybe you could pause it if you want to think about it, but the answer is yes, it is a stopping time because you know when to stop, right? You know when to stop using the first n terms in your stochastic process. The first time you see a number 1, stop. That's it. That's literally it. Now, you might say, really, is that it? Well, yeah, I mean, of course, we can see harder questions, which we're about to do right now, but this is the idea. It's really not that hard. So, some of the questions we're about to do are a bit harder, but let's see if we can do some more like maybe exam level questions. Okay, so let x1, x2, x3, etc. be IID, that means independently, identically distributed, taking values +1 with probability p and -1 with probability 1 minus p. Let Sn be the sum of these random variables, and I'm going to ask you in a second, are the following random variables stopping times? Some of them will be, some of them won't be. Now, first of all, let's just acknowledge something. This is just a simple random walk. So if you've not seen my videos on simple random walks, go and check them out, but you probably have, or at least you know what a simple random walk is. But just to be clear, we're dealing with questions. Some of them are just going to be about the x's, but most of them are going to be about the SNs. So make sure you know about your simple random walks. Okay, let's go. So here's our first one. We're saying that t is the minimum of the n's greater than 0 such that exactly 3 of the x1, x2, x3 up to xn's take the value +1. Is this a stopping time? Pause the video just for a second and think about it. The answer is yes, it absolutely is a stopping time because you can simply count. So maybe x1 does take the value 1, right? And it does. Okay, maybe x2 doesn't. Maybe x3 does. Maybe x4 doesn't. Maybe x5 doesn't. And then x6, maybe that's the third one that you want. So you know to stop. So you don't need to be able to see into the future. As soon as you see that third +1, you stop. So that is a stopping time. Okay, here's our second one. T is the minimum value of n greater than 0 such that xn equals xn plus 1 equals xn plus 2. Again, think about whether that is a stopping time or not. Remember what the xi's actually represent. And the answer is no, it is not a stopping time. Why is it not a stopping time? Well, because in order to know when to stop, you need to be able to see into the future because you only have from 1 up to n. How do you know what xn plus 1 is? And how do you know what xn plus 2 is? You don't. So you cannot call this a stopping time. Not a stopping time. Okay, and finally, t is the minimum value of n greater than 0 such that Sn is bigger than n over 2. So remember, guys, what this actually means. Let's write this down. If Sn is bigger than n over 2, that basically is saying that the sum from I equals 1 to n of the xi's takes a value bigger than n over 2. Is this a stopping time? Well, the answer, think about it. But the answer yet again is yes, it is a stopping time because you can simply look at your stochastic process and you can see, okay, this is the first time that the sum has taken a value bigger than n over 2, therefore it is a stopping time. This one is maybe the hardest to visualize, so I'm going to do a quick drawing just so you can see it, and then we'll call it a day. Okay, guys, so I've just drawn the diagram. Remember that because n only takes positive integer values, I've drawn the line here of Sn equals n over 2, but technically it's not going to be a continuous line, right? It's actually going to be dotted. But just to visualize it, I have pretended that n can just take any value greater than 0, even if it was like a decimal number or something like that, a fractional number. If n was any positive real number, I've just drawn it like this. But in reality, obviously, this is, only for whole number values of n, positive integers. So really, it would just be points looking like this, not a continuous line like that. But I've drawn this for the sake of explaining, because it makes a lot more sense to do it like this. So just to visualize this, let's draw our stochastic process. So one version of it is that x1 is just the value 1. And then we're kind of up here. And now we do have the 1 is bigger than 1 over 2. So we're done. That's it. Okay. So the stopping time here would just be when n is 1. So t would take the value 1 in this case. If n was, if x1 was less, took the value -1, then we're going to be less than it. We're going to be down here. And then maybe something a bit more interesting will happen. But we're basically going to have a process that kind of looks like this. Maybe we've got a couple of +1s, -1, +1 again, and then eventually we do catch up to it, and we get to a point where we're, above it. Let's say so we go up here, and then of course there is a value of n, the next whole number that we are kind of above that. So just to be very clear, remember that the gradient of each of these lines here is either 1 or -1, because for every 1 we go across, we're going to go up by 1 or we're going to go down by 1. So the actual random walk, those lines are going to be steeper than the Sn equals n over 2. So it is possible for our random walk, our simple random walk, to catch up and then go above Sn. It's not like if it goes below, it can never reach it again, because these lines here are steeper than the n over 2 line. So we can go above it. And so hopefully it's pretty clear. There is a first time when Sn is bigger than n over 2. It's well defined, and you don't need to be able to see into the future. So just to elaborate on that, yes, this is a stopping time. And in the future, we're going to see quite a lot of stuff on stopping times. They get more complicated than this. There's a few formulas and theorems and stuff related to stopping times, and we're going to look at all of that in the future. But as an introduction and a vibe check of what they are, hopefully this did the trick. If you enjoyed the video, then please do like, subscribe, and share with your friends, family, and even your enemies. And I will see you in the next one. Cheers.